Hello, hello. Good morning, good afternoon, good evening to our viewers around the globe. I'm so happy you joined us again for our next free webinar. Today I'm here with my colleague Thuc. I will introduce him in a second. Let us, as usual, start with a quick housekeeping, and then we will just dive right into what the energy transition does to existing conventional power plants there. As you know, this is the topic today. We will have a case study about conventional fired power plants. And the topic of today is the key driver digitalization, handle the impact of the energy transition with smart digital solutions. So we will show you the severity of what's happening right now, but we will also offer you a couple of answers and solutions which are simple to do, quick to introduce, and not too costly. Super quick housekeeping. Thuc and I, we are visible, we are recorded, you are not recorded, your name is not visible to anybody, we will not say any names. If you write in the chat, we can see you, we can reply, but nobody else will see it. That's the thing. If you want to talk to us, in half an hour from now, we will join the breakout room. I already posted the link here in the chat, and there you can turn on your camera, you can see us, you can talk to us for 15 minutes or however we need then. But that will not be recorded. So you're totally safe here with us. If something happens, if your audio breaks or the browser is stuck, just refresh it F5 and typically then everything works super smooth again. And now for everybody to see what's coming here in the next minutes, we will have a look at Thuc's bachelor's thesis where he got the grade A recently. So congrats again, Thuc. I was surprised how much potential you could find there by looking at energy data from 3 units in total that you had to look at. The range of what you find was roughly €500,000 per year of saving, up to 1 million, up to 5 million euros per year per unit by optimizing those things that we will see here very soon. Of course, today we will see a bit about STEAG's experiences with the energy transition. That's exactly what STEAG is doing for many years internally for our own projects, but also for our customers and partners around the globe. And we also talk about the impacts on power plants. And I took the liberty to take one piece of information here. You found something. One additional startup could cost as much as 1 hour of operation. We will dive in a little bit deeper there pretty soon. As I said, the smart digital solutions can help owners and operators with many of those troubles. And this is not today to say something bad about either of the technologies. STEAG is really convinced that both together for the bridging period and later on the renewables can play an important role there, but it has to be done right and comprehensive. You cannot just optimize one part of something and ignore another part. So we will see how that all comes together here. Questions anytime in the chat or meet us in the breakout room. One last information before we could deeply dive in. We are happy that around the globe we have customers, we have partners that are striving towards a net zero energy future. Depends on what they are currently dealing with. They might work with us in the terms of conceptual planning and design, plant performance management, asset health and reliability management, or advanced process automation optimization. On the right-hand side, you can see our solution is used widely, so everybody can participate from a strong tool and the knowledge how to use it to solve their problems the best way possible. So that was the last information because we want to really take the time here today to dive into Thuc's thesis. Before we introduce yourself fully, let's give a bit of the background here. You show us a very nice picture from your Ruhr Universität Bochum. I like it very much since I also studied there for my bachelor's and master's degree. Your other university is located in Vietnam, Binh Duong campus. I hope I pronounced it correctly. And for those universities, for your study course, you had the bachelor's thesis of assessing the impacts of energy transition on coal-fired power plants and identifying optimization potential with the chair of thermodynamics here in Germany. So Thuc, thanks for joining us today. Thanks for sharing your insights there that you had over a couple of months working on that data. Now, is there something you would like to add or also introduce yourself a little bit to the audience now?
Yes, thank you, Dennis, for the warm welcome and introduction, and welcome everybody to the webinar. My name is Thuc. I am currently a master's student in computational engineering at the Ruhr University. Before that, I was writing my bachelor thesis also at the Ruhr University at the chair of thermodynamics, as Dennis has said. And before that, I was studying mechanical engineering at the Vietnamese German University in Vietnam.
Cool. Yeah, that's impressive. Yeah, it's a nice track record, and you're still going on. So I'm curious on what you have there in the future also achieved. Now let us dive right in. So what was the goal of your thesis? How did you achieve that, and what have you actually analyzed?
So, as the title of the thesis says, the goal is to show the reader the impact of the energy transition on coal-fired power plants, and one of the main focus point is on CO2 emission and how the integration of renewables into the German national grid affects the CO2 emission from those conventional coal-fired power plants. I combine literature review and thermodynamic calculation to write my bachelor thesis. The data I analyze are from three power plants, one medium capacity of the newest technology, one high capacity also of the newest technology, and the last one is the medium capacity of roughly advanced technology. But for the sake of time, we will not cover that today.
Okay. So how could you summarize the energy transition in Germany, what you found here recently in your activities?
Yeah, so the energy transition in Germany, I say, begin roughly 20 years ago.
Mm.
And as you can see this on this chart, on the vertical axis, you can see the power output from the power plants. Uh, on the horizontal axis, you see the time series. And this chart is recorded from May 2010.
Mm.
You can see that the output from the conventional power plants, such as hard coal, lignite, and nuclear power plant, is dominating this graph. Meanwhile, the output from solar and wind power is very small, very a lot less impactful
Mm.
and dramatic compared to that of conventional power. Another thing you can see is that the load patterns for the hard coal fire power plants, the lignite fire power plants, they are very stable. They are predictable. Um, yeah, I think that is
Good.
good for this slide.
So let's go for a time warp now. 12 years in the future, and it looks like this.
Yes, fast forward 12 years to May 2022, so very recently. You can see that's pretty much the opposite case. The output from the renewables, mainly solar and wind energy, is dominating the grid right now. Um, Meanwhile, the output from hard coal fire and lignite fire power plants, they are really much reduced. And when you look at some specific periods, the output from hard coal fire power plant is almost zero. So
Mm.
this means that the conventional power plants has to be more flexible to adapt to the grid, as the renewables and energy sources, they are given priority to feed their output into the grid.
Mm. Good. So yeah, the remaining conventional plants have to be more flexible here. We see how that impacts the energy generation. But let us look now for the main challenges that the conventional plants face. If the audience has some ideas, what would be the highest level of a challenge, you can just put it in the chat and we will pick it up here. But maybe in the meantime, you can already share your results. What did you find out? What are the things to improve, and where is the potential hidden?
Yes, as I said, the main challenge for conventional power plants right now is the flexibility. And according to the sources I've read, there are three main parameters when it comes to flexibility. You need to reduce the min load. You need to optimize ramping, and you need to optimize startup. And of those three, reducing min load is of the most important. categories.
Good.
Yeah. Also, you need to focus on the thermal stress that comes along with the flexible operations.
Yeah, I will. If we have the time, I will explain the thermal stress in a few minutes. We have a nice graph there, what that also does to the components. But what does that mean for the thermal plants here? Maybe you could have this example with us, or what actually happens to one specific unit, because that's typically what our customers are faced. Yeah, they get some plan what to produce, but it could look very different. So what do we have here?
So for these two graphs, again, they are from the 2015 to 2020 and 2021 in the first quarter of the year. On the vertical axis, you see the relative load of the power plants, and on the horizontal axis, you see the time. And when you compare the two, you can see that in 2015, the output of the power plant is um, flexible, but they are still quite stable with the one or several periods of continuous base load or full load operation. Should I say?
Like
There's
here.
yeah,
I see.
excuse me. Yeah, they are they are also less downtime, and the downtime they are relatively short. Yeah. Um, and then when you compare that to that of 2021, you see there's almost zero continuous operation at full load. And coupled with that, you have sometimes you have a very long downtime in between the startup. Also, the startup happens a lot more frequent and ramping up and down as well.
Right. For now, that's already, it's quite a change, yeah, for one unit. Now let's
Yes.
look how they deal with that. Um, so what can we do in terms of start optimization? What does that mean? What does that cover, and what are possible outcomes?
Yes. So as you can see from the previous graph, the power plants experience about roughly 20 warm start per year on average. This result in the 40,000 tons of CO2 emission during startup a year.
Right.
And correspondingly with that is 15,000 tons of coal being consumed. Of these 40,000 tons of CO2, 12 of those can be removed. They don't have to be there
Okay.
if you optimize the startup processes. And
Mhm.
of course, you optimize the startup processes. You consume less coal, and you reduce the CO2 emission. And all of this will reduce in roughly 360,000 euros per year.
And maybe for the audience to better understand how you got there, I think that was a pretty amazing thing to look at 3 units in such a short time. Let's say like there's three levels. One is the digital measurements that the power plants have already, yeah, most of them around the globe. So you have a DCS, this SCADA system, you record the measurements, you need that to operate your plant anyways. You have some kind of data historian where you would save relevant data. And for example, we are looking for 1 minute mean values for a couple of hundred measurements, and customers can just give that to us, for example, with an interface without a problem over long periods of time. So that is first step, the measurement data. Second step that was helpful here, Epsilon Professional, first principle thermodynamical modeling was applied already to those units, and there was a digital twin that was providing very precise calculations, efficiencies, and so on. So that result information was also available for you. And the last stage, yeah, you took that data, did some statistical analysis with that, some Excel evaluations, even more, just to paint the big picture here. And that is how you could come up with those precise numbers based, yeah, on hundreds of measurements. And I think that's pretty impressive, since it's also scalable, right? You didn't have to make a model for a year first. You could just pick up there. And that's also one of the takeaways for me here today, to see how those solutions work together. And if you have already a certain level of tools, then you can do new stuff in no time. And so I hope that was helpful. Let's go on. But now I think it's more clear now how you could get such precise numbers. And yeah, so sorry for interrupting, but I think that was good for the audience. Let's talk about the next facet here, improved min load flexibilization. Let's look at that.
Yes. So as I've said before, min load is the most important flexible parameters to evaluate the power plant. And to put it simply, min load is the uh, lowest load that the power plant can maintain its operation at. So if you take a look at this graph here, on the vertical axis, you have the unit efficiency of the power plant, and on the horizontal axis, you have the relative load. And what I found out, and a lot of sources found out as well, is that as the relative load of the power plant decrease, the efficiency of the unit also decrease. I think one source point out that if you reduce the load by 20%, the efficiency will drop by 2 to 5 percentage points, if I remember correctly, and which is relatively close to what I found out by analyzing the data. The power plants, they are of the newest technology, but they also suffer heavily. If they reduce their power output from 100% to say 45%, the efficiency will drop from roughly 40% to 37%. Yeah.
Wow. And that's, as you said, that's a pretty new unit that was designed for this kind of operation around the globe. Also, older units are in operation, which were designed for full load only. And so the drop might be much more severe there.
Yeah.
Good. So how could you summarize that case study there of that unit?
Yeah. So in summary, because the power plants had to be shut down more than in the past, there's 40% reduction in its uptime. Along with that, there are 20% increase in min load and part load operation. And as you can see from the graphs before, there are 35 additional startup due to the shift in the merit order rating. From the graph, you can see also that the average unit efficiency is dropped by 1.2 percentage point due to the increase in part and min load operation. And because of this reduction in efficiency, you are spending more, you're putting more energy in to get the same amount of electricity out, and that result in additional CO2 emission. For this case, is 150,000 tons of CO2 per year. And if you can manage to optimize the efficiency just for min load and part load operation, you can save roughly 1.1 million euros per year.
Wow, yeah. And when I was bugging you in the preparation, first you said this is like a conservative estimation here, and so we were playing around. What if everything could be utilized that is in the data? Up to 5 million euros per year were possible in this example here. Of course, in the reality, not everything is possible, but this is just to show there's a huge impact of optimization of those things. And yeah, if somebody in the audience says, well, I don't have this, I don't even know how many startups I have, since the classification is not so easy. That's all the tools that I mentioned before. We can talk, we can help you. You might just get one piece of our toolbox there that helps you on your journey there. So this is more or less an invitation for further discussions. So let us know if we can help you with any of those issues. Oh yeah, now about the thermal stress. If you push an old unit to its limits, let's look how that results in limitations. Yeah. So, and as we discussed before, this one I will share, since it's I was part of the guys that came up with that explanation. two phases here. Right now we see the old world, the base load scenario where a plant is operating. Typically power plants are designed for an operating hour amount, so 200,000 hours of operation is typical for the design of power plants. We have two mechanisms. If you like it, audience, let us know. We can share a full webinar about that. It's a very interesting topic, at least for me. Those two mechanisms, creep and fatigue, those are affecting your material, your metal. In general, that's thick-walled components, so big collectors and so on, where it's hot inside when you start up, it's cold outside, so you have stress in the material. It's easy to understand. And so one mechanism is the creep that is mainly depending on the temperature and on the pressure. And the other one is the fatigue that comes from the changes of your operation mode. And now if you follow me here, that 100% is like a mathematical and engineering approach to say one component is at the end of its capability. It is not 100% precise. It will never break here just because some number is reached. But that is how you look at the power plants to find out where to focus on, where the trouble is, where you need to inspect and so on. So we have for the thick-walled components even software ready SR1 that is just doing that online, and you can always see when something goes bad. If you sum those two up, that's the thermal stress or total lifetime consumption. And so in the old world, you would assume a certain amount of startups per year, let's say one hot start per year, for example. And with that load scenario, you reach, let's say, 80% here of the calculated structural damage. And now energy transition happens and your unit needs to be operated more flexibly. What you can do, what you can deliver. So you do that and suddenly the fatigue increases a lot over time, because you start up and shut down much more often. The creep, on the other hand, since you have lower operation hours, it's less, but the sum goes up, and that's what we want to show here. It doesn't mean it breaks here. You might need to replace something, but you need to pay more attention, more effort, find out what it costs you to be so flexible. And so if you have the data, as I said, digital data, some historians, some evaluation there, then it's much easier to determine and assume how much it costs you to be so flexible. And we are helping our units and customers to have the deeper insight here. If you need that kind of insight, let us know and we can have a talk about that. So that happens to your unit if you have to be more flexible than before. So I hope that was understandable. That was a shortcut of an hour of a presentation sometimes we have with lots of explanations. Thuc, let's go back to you. Let's talk about further insights. What did you discover on your way and dealing with the data and the energy transition?
Yes. So there are currently multiple countries pursuing energy transition, and each they are facing their own challenges. For example, Vietnam or Southeast Asia in general, they are pushing, like Germany, they are pushing the more renewables into the grid. But the problem that Vietnam is facing is that the national grid right now, there is not capable of transmitting the electricity from the central highlands, which is where they put the solar farms and the wind farms, because they have they have the highest potential for energy production. The grid is not capable of transporting electricity from that region to the industrialized north and southern region. And meanwhile, India is still, at the time of my thesis, India is still trying to build more coal-fired power plants, even though it may result in those power plants being utilized with capacity factors of 45 to 50% only. One really interesting country that I found that is conducting energy transition is Australia. Australia, they once introduced the CO2 emission trading scheme similar to what the European nation has. But I think it was in 2012, but then in 2014 they removed it, and immediately the amount of CO2 emission increased again.
Wow.
And you need to keep in mind that Australia is the country with the highest amount of solar radiation, so they are really suitable for solar power.
And there should also be enough space to set up the PV.
Yes. Of course, integration of renewables force conventional power plants to be flexible because the output you cannot always expect the sun to shine or the wind to blow. So the power plants, the conventional power plants, has to be flexible enough to adapt to the remaining load requirement of the grid, so to speak. Of course, it goes without saying then flexibility is the most important aspect of power plants, with min load being the most important criteria.
Yeah, what you just mentioned there, I think that was for me so interesting to see. You used Germany and the data you saw here as a template and apply that to your country, to Vietnam, also for other countries that are on a different part of their journey, but the challenges are similar. If you say grids are not fully capable to transfer the electricity, sounds a little bit familiar here too for me in Germany. We're also talking about grids for many years and improving in some lines and then having the wind from the German ocean, yeah, to BMW production facilities in the southern part. So I think the challenges are similar, even though they look different in all the countries. So it's not one solution, not one thesis answers all the questions, but the toolbox is pretty helpful there to come up with the right answers. Good. So I think there's one slide to summarize here what we discussed, and then we can jump into the breakout room together. How to handle those impacts. And I think we showed pretty amazingly how huge they are, how much there is to save if you have the right tools and if you see it. So first of all, what we would like to bring to the table there is 20 years of experience in handling the energy transition, since we are doing that for so long here in Germany already. If you are looking for decarbonization, we are there to help you to reduce your CO2 footprint by optimizing your operation. Apply this epsilon model to your unit, see exactly what's going on, where currently problems are. That will definitely help you with your CO2 emissions. And they're also getting more costly by the hour, more or less, right? So costs and fuel costs, CO2 costs, plus saving energy is pretty important. On the right-hand side, digitalization. With the latest technologies, you can boost your asset performance. You can even, with our digital twin technology, find out there's something wrong 2 months before it's actually happening. So this is all time you can use to fix something and be smarter, and don't track faulty measurements every time you look for a problem. No, that is all. Let us show you what is available, what we apply, what our partners apply to really tackle those issues with ease and time ahead. And the last one, I think that's a good message. If you don't know what the political situation is, how long your power plant will operate. And I can tell you, this is currently what we are facing here in Germany, that you don't know exactly how long it will go, depending on the current situation. You will not make a large overhaul, spend a lot of money, 10 million euros for, I don't know, new turbine or whatever. This software that we showed you here, that we mentioned, those modules, they are in comparison pretty cheap. They have a short ROI payback period of less than 1.5 years, according to what you can solve with that. So let us know. Here's our contact data. You can reach out anytime. We have more videos available for you to learn more. And if you think that could help you with what you are currently looking at, let us know. We are from system technologies here from STEAG, but we have other departments that could, for example, help you optimizing your DCS to be more fast when you start up. So that is just to let you know what's possible. Now I would like to give back the word maybe quickly to Thuc. Anything else needs to be addressed from your side here in the big meeting?
I think that would be all, Dennis. I just would like to say thank you to the audience for their time and their attention.
Absolutely. Yeah, it's good to see a couple of familiar faces here. At least your names I can see. I will talk to you later then. So now everybody in the chat, I will just put it again. If you want to say hello without any recording, you can just follow this link here and we will be there for 10-15 minutes and we can have a quick talk. Also, any questions that you have for Thuc, we can talk about there. Thank you for now. It was a pleasure. Thank you, Thuc, for sharing. And everybody, see you next month with the next webinar. Bye-bye.
Goodbye, everybody.